All right, we're going to wrap up the nomenclature part of this chapter. And just to give you a heads up, this will probably be a little bit longer of a video. So if you find yourself getting distracted or mind wandering, just feel free to pause, take a break. But I am going to kind of finish up nomenclature um, in this lecture. So we did a bunch of problems before, and I want to highlight one more kind of common, I don't want to call it an exception, but something that does pop up from time to time. And that is, what if your substituents have branches? Or what if your substituent has a substituent? How do you treat that? Quite often they can be handled in a couple of ways. A lot of them have a common name to them. So that's these here. I will talk about these in a second. I'm going to kind of skip over it and then I'll come back. But the one method that will always work is to kind of treat that side chain as a little mini parent. And here's what I mean by this. So if we look at this compound here, or this structure, this is our parent chain. And hanging off the side here is a side chain that also has a branch on it. I'm just going to put a box around there. So the way that you treat this is you give the carbon that's attached to the parent chain, I'm going to put a big dot right there. You automatically make this number one. And then you just keep on going until for the longest part of the side chain. So in that case, two. And hanging off of that number one carbon there, the one I put in a box, is a methyl group. So I'm going to name this side chain 1-methyl ethyl. So ethyl refers to the two carbon part, the one and the two, and then the 1-methyl means that there's a methyl group on the number one carbon. So when I put this in the name, so let's just number our parent chain here. On the number 4 carbon, there is a 1-methyl ethyl group. And we put the whole thing in parentheses there just so that there's like no confusion. And then our parent chain is octane. Now, this particular branched side chain, 1-methyl ethyl, has a common name that's called isopropyl. So the common name for this is isopropyl. So you'll notice like there's 3 carbons in there, but it's not attached to the carbon on the end. It's attached to that middle carbon. And so that's why we call isopropyl, not a regular propyl group. A regular propyl group, I'll just redraw this here, has 3 carbons in a row like this. So kind of note the difference between isopropyl and a normal propyl. So what I recommend is I have I'm gonna have a list here on this page and subsequent pages, memorizing these branched side chains. And I want to highlight that in this list I put up here, these bolded letters are the ones you would use when it comes to alphabetizing. Okay, so this requires a little bit of memorizing when it comes to those side chains, but you should also know how to name them with the systematic naming system and not just a common name. So I kind of again, I'll just highlight some of the list here. So isopropyl, we just kind of went into the common, or I'm sorry, the systematic name would be 1-methyl ethyl. These three here for 4 carbon atoms, sec-butyl, isobutyl, and tert-butyl. So again, with these, we would name it based off of, or we would alphabetize it based off of B for this one and B for tert-butyl. But for isobutyl, we name it off of I. Now let me kind of show you what those groups look like in a compound. So I'm just going to do a large carbon chain here. Don't know how many carbons that is, but oops, it disappeared. Okay. And so a sec-butyl group would look like this, where the that side chain is attached to the parent chain by that second carbon there. An isobutyl group would look like this. So note where that group is attached. And tert-butyl, I'll draw it over here, looks like this. So it's a group of 4 carbons, but note how the carbons are arranged. So it's very important to know the difference between those 3 types of butyl groups. And again, if all, if all everything else fails, just default to the systematic naming. Just, like the sec-butyl group would be a 1-methyl propyl group, because that's going to work 100% of the time. And then for a 5 carbon chain, pretty much the 2 that I want you to know are here. So isopentyl, okay, it's also known as isoamyl, and then neopentyl. Make sure that you know those 2 as well. Again, I'll just demonstrate what those might look like in a compound. So I'm just, again, going to just draw a large carbon chain. And so um, let's see, isopentyl would look like this, and neopentyl would look like this. All right, so let's do a little practice with these branched side chains. So first thing, we're just going to kind of go, from our basic rules from the start. So first thing, let's just identify and name the parent chain. Right, find the longest chain of carbons. Okay, and so that's going to be this chain right here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the name of that parent chain would be undecane. Now we have a couple substituents here, and what we're going to do is name them in both manners. So this substituent right here, its common name would be isopropyl. So I'll just put C for common. Its systematic name would be 1-methyl ethyl. So I would number it like this, 1, 2. Now this group down here, the common name would be sec-butyl. Its systematic name would be 1-methyl propyl. Now, when you use those names, those systems, don't mix and match. Don't use the common name for one and systematic name for the other. Either make them both common or both systematic, but don't mix them. And you kind of see why, because the alphabetizing works out a little bit different. But let's start off by naming this with the common name. So that should say common there. So when I'm going to number it, 1, 2, 3, 4, 1, 2. So I'm going to number it like this. 1, 2, 3, 4, 5, 6, 7. And so when I compare the alphabetizing of isopropyl, I use the I, and sec-butyl, I'm using the B. Sec-butyl appears first. So 7 sec-butyl, and then 4 isopropyl undecane. Now let's name this. So that's using the kind of common names. Let's use the systematic names. Now notice here the alphabetizing is going to be different, because methyl ethyl. So both of them have methyl to start with. But one is ethyl, E, the other is propyl, P. So this group will come first for 1-methyl ethyl, and then 7-1-methyl propyl undecane. All right, so let's look at another practice here. Now, you don't have to worry, we are not going to name this whole thing. All we're going to look at here is how would we name this as a branched side chain? Now, I know there's like some new like what the heck are these bonds, like these wedges here. Don't worry about that right now. I'll eventually get to it. We'll talk about it in this lecture and in subsequent lectures. But right now we'll just kind of count these here. I'm just going to write these in as methyl groups. And we're just going to name that side chain. So it's connected to this carbon. And so that means I'm going to start by numbering here. 1, 2, 3, 4, 5, 6. Just like if I were making a parent chain. So I go to the longest direction or the longest continuous chain of carbons. And so notice I have on number 1, there's a methyl, and number 5, there's a methyl. So the name of this side chain would be 1,5-dimethyl, and then hexyl. And then if we were going to put it in the whole name, we would just put it in parentheses. All right, now also within the alkane family are cyclic alkanes. These are carbons that are connected end to end in a ring. So for example, if I were to take propane and somehow connect the two ends together, it would make a cycloalkane. And now naming these is really simple. We just put the prefix cyclo in front of it. So this would be cyclopropane. And cyclic alkanes, their skeletal structures adopt the however many carbons they have, we make that kind of member of a ring. So like if we took pentane and made it into a ring, connect the two ends, we'd make a 5-membered ring, which is a pentagon. So we would call that cyclopentane. And that becomes the parent name. Now, rings get a little tricky because you have to compare, if the ring has a substituent, you have to compare what's bigger. Is the ring bigger or is the side chain bigger? So if the ring has more carbons, then this is our parent chain, and we name whatever is left as a substituent. So that 3 group of carbons right there is a propyl group. So I would call this propyl cyclohexane. Now, if there's only one substituent, I don't have to put a number because it's automatically assumed where that one substituent is automatically the number 1 carbon of the ring. So this carbon right here that I'm putting a dot on is automatically attached to the number 1 carbon. So putting 1 propyl is redundant and not needed. We'll talk about what do I do if there's more substituents, but if there's only one, you don't have to put a locator number. Now, what happens if the side chain has more carbons in it than the ring? So here we have a 3-carbon ring, but 1, 2, 3, 4, 5, 6 carbon chain. So now the chain is our parent, and the ring we treat like a substituent. So normally we would call this cyclopropane. So we drop that ending and add YL, called a cyclopropyl group. Now, in this case, we are going to number the chain because I'm defaulting to like just the regular rules that we've talked about. And so we would name this one cyclopropyl. There's our substituent on the number one carbon. And then hexane is our parent chain. So let's get a little bit more practice with all these things that we've talked about. So what do we do if there are more than one substituent? So what I'm going to do is kind of, I'm going to draw another problem in here. And let's deal with what happens if there's two substituents. So my parent chain here is going to be the ring. And on this carbon, I got a chloro substituent. And on this and over here, I have an ethyl substituent. Now, because those groups could be put in any number of arrangement attached to cyclohexane, I do need to give it a locator. I have to number them. And so how do I number these? I'm going to default again to like my normal um, the normal rules where the substituent encountered first gets the lowest number. But that means I could do this, 1, 2, 3, or I could go the other way, 1, 2, 3. So how do I do this? Because in one situation, the chloro is 1, ethyl is 3, and vice versa. So when it comes to two substituents, and write this down somewhere in the margin, for two substituents, this is the only time alphabetizing relates to numbering. This is, as I said, this is the only time where the alphabetizing dictates the number. So the one that appears first in the alphabet gets the lowest number. In this case, chloro gets 1, and then I number ethyl so that it gets the next lowest number. Notice here I'm going clockwise. If I went the other way, that number would be 5. That's not what I want. I want to get the next lowest possible value. So when I name this, I have 1 chloro, 3 ethyl, cyclohexane. Again, I want to highlight this is the only time alphabetizing dictates the numbering system. You'll never see that for any other. In fact, when we go to more than two substituents, then we're just back to it's coincidence if alphabetizing and numerical order is the same. But the main goal is we want the lowest possible combination of numbers. So let's just name our substituents here. I have ethyl, and then methyl, and then chloro. So this is a little bit of trial and error in the beginning. After you do these enough, you kind of like are able to look at it and just kind of know right away what that lowest possible can be. But I'm going to kind of go through some cases here, like what if methyl were number 1? Okay, so if that were the case, that would be the numbers would be 1, 2, 3, 4, 5. That's how I would number it. So one combination is 1, 2, and 5. Okay. Well, let's look at another possible combination here. What if I did, what if I made the no, sorry, that's not an ethyl group. That's a propyl group. Sorry. If I made the propyl group 1, 2, 3, and 4. Okay, that's a better combination than 1, 2, and 5. All right, well, what if I did one more here? If I start with the chloral, 1, 2, 3, and 4. Well, 1, 3, and 4 is not as good as 1, 2, and 4. So that's the numbering system I'm going to use. I'm going to say this carbon with the propyl is 1, this carbon with the methyl is 2, and that carbon with the chloro is 3. And now again, I'm going back to alphabetizing. Chloro appears first in the alphabet, so it's first in the name. Or chloro, then methyl, then propyl, cyclohexane is the parent name. Right, let's do some more practice. Now we're going to kind of put all of this together. Okay, so starting at our very foundation with letter A here, find the longest possible chain of carbons. Now, I'm just going to kind of highlight what that is without going through all the options, but I recommend that you go through it as well. Um, the longest chain of carbons here is 8. And then I'm going to number this from left to right here. Now, if you are wondering, well, why is that? If I go the other way, this methyl group here is also on number 3, but this gives this methyl 3 and this methyl group the next lowest possible value. So that's why I'm going from left to right. So I have methyl groups on 3, 4, and 6. So 3, 4, 6. Trimethyl octane. And again, I use that numerical prefix because I have to tell the reader that there's 3 of the same group, 3 methyl groups. Now, in the next example, in B here, I have a 6-membered ring. That's bigger than the side chain. So that's my parent chain. And so the group hanging off is our substituent. And notice it's branched. So I can name that either using the common name, which that is a sec butyl group, or the systematic name, where this is 1-methyl propyl. Okay, so I'll just name both of them or use both versions. So one name would be sec-butyl cyclohexane. The other name would be 1-methyl propyl cyclohexane. Again, since that's the only substituent on the on cyclohexane, I don't have to number this carbon right here. It's just automatically assumed wherever it's at, that's number 1. All right, and then finally in C, this is going to be our parent chain. And I'm going to number it so that the substituent encountered first gets the lowest possible number. Now, what I'm going to do before I finish this, I'm going to redraw this over here. And I'm not going to answer this on the video. I want you to think about it. Why didn't I do this as my parent chain? That's 7 carbons as well. So I want you to think about that. All right, so on this carbon, I got a methyl. This carbon, there's an ethyl, or on number 3. So I alphabetize the substituents, 3-ethyl, and then 2-methyl, and the parent chain is heptane. All right, let's keep on going with some more practice. I'm doing a lot of examples because this is such an important foundational concept in OChem. We're going to be doing nomenclature nearly every chapter that we cover because most of the time, not all the time, we introduce a new functional group. You need to know how to name them. So getting these rules down now is going to save you a lot of grief and agony later. Okay, so now I'm going to find my parent chain here. And in this case, it's going to be this. 1, 2, 3, 4, 5, 6. And again, I want you to ask yourself the question, why didn't I just go straight from left to right? Okay. So if you can't answer that, then review your notes. Come talk to me in office hours. So then I'm going to number this because those two methyl groups are encountered first. So there's a methyl and another methyl. And then over here is an ethyl. So ethyl's higher in the alphabet. And then we're going to name our two methyls. Each methyl, when they're on the same carbon, gets its own number. We have to say 2,2-dimethyl. And then 6 carbons is hexane. All right. Now with letter F, kind of hit an interesting situation. There's a 6-membered ring here, but there is a much longer alkyl chain. So because of that, I'm going to treat this not as the parent name, but as a substituent. It will be called a cyclohexyl group. And then I'm just going to number these 1, 2, 3, 4, 5, 6, 7, 8. And then over here is an ethyl. And then we got a couple methyl groups here. Now, when it comes to alphabetizing with cyclohexyl, the C is how included in the naming. I'm sorry, the alphabetizing. So C comes first in the alphabet. So 2-cyclohexyl, and then ethyl's next in the alphabet. 4-ethyl, then 5,6-dimethyl octane. All right, and then finally, let's find our parent chain here. Now this one is super complicated because there are a lot of different pathways that have the same parent chain. But by going this pathway, 1, 2, 3, 4, 5, 6, 7, we create more substituent or the most number of substituents. I encourage you to kind of look at the other pathways and see if you can, find the options that don't work. Um, but again, like when you have two or more pathways that have the same parent chain, you go with the pathway that gives you more substituents. So I'm going to number here 1, 2, 3, 4, 5, 6, 7. So let's see. On 2 and 5, well, actually, let me just label these. So we have an ethyl here, and then there's a methyl here. This is a regular propyl group, and then this is another methyl. Okay, so ethyl comes first in the alphabet. Let's say 3-ethyl. Then methyl. So 2,5-dimethyl. I have to indicate that there's two of the same group with that prefix of di. And then on 4 is a propyl. And then heptane is the parent chain. Now, we've done quite a few problems where we are going from structure to name. Let's go the other way now. And in my opinion, this is a little bit easier because all you have to do is start with your parent chain and just draw that. So just draw pentane, 5 carbons. And then I'm going to put my substituents where they're supposed to be. The hardest part is knowing what that substituent is. So on the third carbon, if I number like this, 1, 2, 3, 4, 5, I'm going to put an isopropyl group. And then on carbon 2, there's a methyl. And carbon 4, there's a methyl. So let's do the same thing for B. Again, find your parent chain and just draw it. I'm going to do that over here. 1, 2, 3, 4, 5, 6. 6 carbons. And I'll just number it this way. So on carbon number 4, I'm going to put an ethyl group. And on carbon number 2, I'm going to put a methyl group. And then finally, on the last one, my parent chain is cyclopropane. So remember that cyclic alkanes, you draw their skeleton structure is drawn in the same shape of however many carbons they have. So cyclopropane has 3 carbons. I'm going to draw a 3-sided figure, which is a triangle. And then this will be number 1, 2, and 3. Doesn't matter where you start. I just kind of pick that top one. And so on 1 and 1, there's 2 methyl groups. And on 2 and 2, there's 2 methyl groups. Now, probably one of the most confusing types of compounds to name are what are called bicyclic compounds. Bicyclic compounds are 2 or more rings fused together. And so if you look at this structure on the left, you can kind of see like there's this 6-membered ring like right here, and then you got this like this bridge right here connecting the two. Now the simple, I don't want to say simple, the first thing is that the prefix for these compounds, instead of cyclo, the prefix changes to bicyclo. Now, here's where we run into problems, and this is what makes this like in my opinion, kind of the trickiest things to deal with, is count the number of carbons that are in each of these. So I'll give you a second to count. You see the one on the left has 7 carbons. The one on the right has 7 carbons. So if I just start calling this bicycloheptane, which one's bicycloheptane? Well, they're both bicycloheptane, but they both look different. They are not the same compound. These are technically constitutional isomers. So there's a nomenclature system that we use to differentiate between these. And what I want, the way that we do this is the process, I want you to mark these 2 carbons. These are called bridgeheads. Mark those 2. And what we're going to do is going to go in each direction and count how many carbons it takes to get from one bridgehead to the next. So what I'm going to do is I'm going to go from this bridgehead this way to this one. And notice I hit 1, 2 carbons. Now I'm going to do the same thing for the other one. I'm going to go this way. And this direction I hit 1, 2 carbons. And then finally, I'm going to go this way. And I hit 1 carbon, that one kind of sticking out right there. And we incorporate those number of carbons that I marked there into the name. Here's how this works. I start with my prefix bicyclo. I'm going to put an open bracket, and I'm just going to put some numbers in. Those numbers are equivalent to how many carbons are in each pathway. So in the red pathway, there were two. The blue pathway, there were two. And the black pathway, there's one. I separate each of those numbers with a dot, and then I put heptane. So that basically tells the reader that in this bicyclic compound, in one pathway, I should have two carbons, another pathway should be two, and in the third pathway, there should be one. Let's contrast that with the other side. So again, I'm going to mark the bridgeheads here and here. And I'm just going to start at one bridgehead and go around the ring until I hit the next one. So for this one, I hit one carbon there, put a circle around it. Now I'm going to do the same thing here. I'm going to start here, go there, there's one carbon, go here, there's a second carbon, go here, there's a third, and then I get to the other bridgehead. And then for the last pathway, I go this direction, there's a carbon right there, and then I hit the bridgehead. So I have 3, 1, and 1. And so the name for this bicycloheptane would be, there's my brackets, 3.1.1 heptane. Now, probably the most confusing part of this is what happens if there are substituents on the bicyclic compound. Because we got to not only name a substituent, we got to give it a number, a location, because it could be anywhere on those 8 carbons. So again, this might take a little trial and error in the beginning. After a while, you might be able to recognize it a little bit more quickly. But you always give one of the bridgeheads the number 1. That's where you start counting. Okay, so I'm going to start here. Actually, I'll mark it with a different color. And I'm going to give that number 1. Now, I can either go this way or this way. So, or like that way with my numbering. The proper way is to go towards the pathway that has more carbons in it. So notice this pathway here has 1, 2, 3 carbons in it. This pathway has 1, and this pathway has 2. So the convention, again, don't get mad at me. I didn't make the rules. The old guys at the IUPAC convention, this is the way they said it should be done. So I'm going to number this way. And I just go around, and then I give this peak at the top the last number. So I would call this 6-methyl. There's my substituent on 6. Bicyclo 3.2.1 octane. Now, the question you might have in your head is, why did I start with that bridgehead as number 1? So I'm going to try to redraw this here. Oops. Okay. So why did I start with, when did I start here? Here's my methyl group right there. I'll just put a CH3 so I don't mistake it. If I start here and I use the same convention, remember I have to start numbering towards the longer pathway. That's going to be this direction. And when I do that, the methyl group ends up on 7. So that's why I don't use this pathway. So again, it takes some trial and error in the beginning to know which direction to go. After you do a handful of these, though, it kind of becomes a little bit more obvious which way you should be numbering them. And that's where we're going to conclude with this. That kind of finishes our nomenclature discussion. And again, apologize, the video might be a little long, but like as I said before, hopefully you've taken some breaks, go back, redo some of the problems, go through some of the problems in a textbook. Nomenclature is super, super important. But that is where we will stop here.